Okay, so we are going live now, and we will start with this new IPARCOS astro-seminar, the last one in this autumn period. And today it is a pleasure to introduce Loic Hausammann from the, now working on a private company, but with his research on the EPFL in Switzerland. Loic did a master thesis on plasma physics in Princeton Plasma Physics Laboratory in 2015. And after that, he moved to Switzerland to start a PhD under the supervision of Yves Reveap on simulations of low mass galaxies, of dwarf galaxies. And he presented his PhD recently in this autumn, just a couple of months ago. So today he's going to present us very new results from his research. And as I told you, sadly, we lost a very good researcher because he left astrophysics and he moved to the private company, in where he will, of course, do a very, very good job, as he's an expert on all this machine learning related physics that he did in the PhD. So please, if you need to add something else, Loic, to your presentation, do it with no problem. And thank you a lot for accepting the invitation and giving us this very, very interesting talk. Thank you, and you can start when you would.
So thank you very much for this nice introduction, and thank you very much for the invitation. So yeah, I think you said everything, so I won't have to add anything. So I can directly start with my presentation. So today I will present you two different topics. So the first one is a study on the RAM pressure stripping applied on dwarf galaxies, where I will try to show you how important it is to use high-resolution simulations to understand what is going on. In the second part, I will present you a new approach of writing the output of our simulation that enable us to reconstruct the state of the simulation at any time with high accuracy and for lower storage costs than snapshots. So let's start with the RAM pressure stripping. So in the 90s, physicists have been looking at the distribution of satellites around Milky Way-like galaxies. So they ran dark matter-only simulation and compare with observation. And they quickly realized that we had far too many satellites in our simulation. So they started to work on adding new physics to try to solve this. So mainly adding the baryonic physics. And today you can see the kind of distribution we have on the right. So you have here in blue the Milky Way. So it's the distribution according to the magnitude of the satellites. And here you have, this is the Milky Way and this is Andromeda. And you can see in white TNG 50 that is able to reproduce correctly the distribution. But it's not the only code. You have many others that are able to do so today. So through those studies, we have been able to see how much the environment impacts the number of satellites. But we have some other studies that look at the properties of the dwarf galaxies according to the environment. So here you have what we call a morphology density relation, where you can see the distance to the host. So in this case, it's the distance either to the Milky Way or to Andromeda. And on the y-axis, you have the amount of H1, so the cold gas. As you can see, all the dwarf galaxy represented here shows a strong correlation. The closer a dwarf is to the host, the less gas it has. So the environment does not only impact the number of satellites, but also the properties of the satellite. And to explain this, we usually use two different processes. The first one is the tidal stripping, so a purely gravitational effect. So here it's illustrated with the Sagittarius dwarf galaxy that is being destroyed by the Milky Way. And we can clearly see an overdensity in object here that is due to this tidal stripping. And it's only efficient at very low distances. So we need an additional process that explains what is going on in the previous graph at long distances. And that's the ramp pressure stripping. So the idea of the ramp pressure stripping is very easy. You have a massive galaxy, more or less like the Milky Way. And all around it, in blue, you can see the hot halo of gas. It goes far further than that, but due to the detection limit, we cannot see it. So if you have a satellite around this massive galaxy, you will have some hydrodynamic interaction between the hot halo in blue here and the gas within the satellite. And so it's mainly through friction and collision, and that's called the ramp pressure stripping. And what happens is that the gas is being removed from the galaxy. So as shown here with the jellyfish galaxy that is going to the top left corner, and you can see in purple and red the gas leaving the galaxy due to the ramp pressure. You can also see it in 3D here. Oh, you cannot see the movie. Sorry for this small problem. I will try to quickly fix it. So sorry, I have to share my two screens in order to show you everything. Why? What is going on? Okay, perfect. So you should be able to see the simulation now. Sorry for this small problem. So at the center, you have a Milky Way-like galaxy, and it's surrounded by many dwarf galaxies, the small red dots. And what is interesting in this movie is all this white stream you can see, that is simply the gas being removed due to the ramp pressure stripping. And something very important to understand is the difference of pressure we have that are shown right now. And they come mainly due to the difference of temperature that are shown now. So it's very, very important to understand that we have very cool gas with temperature going as low as a few Kelvin in blue and within the galaxies. And in yellow, you have the hot halo gas that has temperature going up to 1,000,000 of Kelvin. So before showing you my results, I just need to present you the current state of our knowledge. So here I will present you what I call the classical point of view. So we start with a dwarf galaxy at the outskirts of a host, and this dwarf is infalling into it. So you can see the time passing from top to bottom. And if we focus on the dwarf galaxy, we can see clearly here that the galaxy loses its gas very quickly. So if we look at a graph, we have the following things. So here you have the gas fraction as function of time, and a very typical situation is a blue line that you can see here. So as you can see, as soon as the host starts impacting the satellite loses all its gas. And by losing all its gas, we also stop the star formation. But some other simulations are predicting exactly the opposite. So here you can see the star formation rate as function of the time. And so the dashed line here shows you a simulation run in isolation, so without any ramp pressure. And then you have here the same simulation run, but with the ramp pressure stripping. And as you can see, this ramp pressure stripping can produce an enhancement of the star formation rate. So we have those two different pictures, one that tell us that the ramp pressure stripping is very efficient and quench quickly the dwarf galaxies, and another one that tell us that we can have an enhancement of the star formation rate. So in my thesis, I try to understand what is going on, and I try to give an answer through a study of the cold gas. And to understand why this cold gas is important, we need to understand what we call the artificial collapse. So the idea is very simple. If you have a homogeneous cloud, gravity cannot make it collapse because there is no seed on which to grow the instability. But due to the numerical noise, we have some small perturbation that makes the cloud not so homogeneous. So the gravity can collapse an homogeneous cloud if we do not have enough resolution. So to prevent this, we change slightly the hydrodynamic equations when we lack the resolution. And to figure out when we lack this resolution, we use simply the Jeans mass that is given here and the relation between the mass of our particle and the spatial resolution of the particle. And by putting the two together, we have a direct relation between the internal energy of the gas and the density of the gas. So in practice, you have this kind of situation. So here I'm showing you an Eagle simulation as function of temperature and density. The relation is shown here in green. So everything below this line is not well resolved. Everything above is fine. And so to change the hydrodynamic equations, what the Eagle team is doing is they increase the energy of all the particles that should be in this lower part. So you can see many particles lying on this line. So that's one of the techniques. It's called energy flow. It's not the one I'm using. I'm using what we call the pressure flow, which is exactly the same idea, but we do not change the internal energy. We change directly the pressure in the hydrodynamics equations. There is also a third method that is worth mentioning. That's the one from Volker-Springel. So the idea is to have a subgrid model within each particle, where you have some gas with a low temperature here and some gas with a high temperature. And so through a few equations, he's able to find an equilibrium temperature that is given by this line. So we have three different methods that impact the cold gas, and this impact is very important, as I will show you. But first, I want to show you what is going on with dwarf galaxies. So here you have one of my simulation. So now you have the internal energy and not the temperature, but it's more or less the same. So here on the right, you can see a lot of gas in a dense phase and very different internal energy. And this is the gas that is within a galaxy. I'm showing you three different lines that are taken from the previous relation I've shown you. So it's internal energy flow. The two upper lines are directly coming from the two previous simulations, the one that shows a very efficient stripping of the gas and the one that shows an enhancement of the star formation rate. As you can see, both of the simulations do not include a lot of cold gas because they do not have the resolution. So you can see the third line, which is my own simulation at higher resolution that allows me to probe a bit more the cold gas. So to study the RAM pressure stripping, you have two different approaches. You can either use a cosmological simulation that allows you to have a self-consistent environment, but it's very hard to have high resolution. And you have also no control on the RAM pressure parameters. So I used a second technique called wind tunnel. So it's exactly like in engineering, when you study the aerodynamics of an object, you have a tunnel where you inject some wind and remove it on the other side. And this allows you to have very high resolution and to have a full control on the RAM pressure. So it was implemented in the code here based on Gadget 2. So we use SPH, but with a modern formulation called pressure entropy that allow us to simulate discontinuities. And being able to simulate those discontinuities is very, very important because the RAM pressure is a study of discontinuities. We also include what we call the radiative cooling. So that's simply cooling and heating of the gas through interaction with photons, so absorbing or emitting photons. And the absorbed photons are coming from what we call the UV background. We also have a very important element called hydrogen self-shielding. And the idea is simply that when your gas becomes very dense, it becomes optically thick. So it prevents the radiation to heat it. We also have these pressure floors that I've mentioned before. And for the stars, so we have a very classical star formation. So it's called stochastic. The idea is simply to convert gas particles into stellar particles whenever some physical equations are met. So I was saying we have this classical star formation, and when the stars are formed, they evolve and then explode in individual supernovae of type 1a and type 2. Those supernovae eject energy and metals, and then when the metals are within the gas particles, we smooth them with a scheme called smooth metallicity. So the last thing I need to mention before showing you my result is the initial condition I'm using. So in wind tunnel simulations, people are usually using analytical models, but that's not what I'm doing. Here I'm taking galaxies that have been shown to be realistic. So cosmological simulation producing those realistic galaxies that I've extracted at high redshift. So you can see on the right the properties. So as you can see, we have quite a short star formation rate. But even if it's short, as you will see, my results are good enough to understand what is going on. In a second part, I will use a more massive galaxy that is shown here with a more extended star formation rate. So before showing you my figures, I just first need to show you a movie. So here I will show you a typical situation for the ram pressure stripping. So you will have some wind coming from the left and leaving on the right. I will not show it. We just want to be focused on what is going on for the dwarf galaxy. So the colors indicate the type of gas. So in orange, you have all the gas with a temperature above 1000 Kelvin, and in blue, all the gas with a temperature below 1000 Kelvin. So as you can see, very quickly, you have the hot gas that is being removed. So if you have a low resolution simulation, so without the cold gas, you will very easily conclude that the ram pressure stripping is efficient at removing the gas within dwarf galaxies. But if you have a high resolution simulation that includes the cold gas, you can have a very different situation, as you can see it. Here, we keep the gas for a very long time, so we can also form stars for a very long time. And to understand what is going on, I need to mention the different pressure we have in place. So of course, we have the ram pressure, that is simply given by the density times the velocity of the satellite to the square. But something people often forget is that we have this thermal pressure. As I've shown you in the introduction, we have very, very different temperatures around the Milky Way. So the hot halo has temperature of 1 million Kelvin, and the dwarf galaxies can have temperatures of a few Kelvin. So we have these thermal pressures that can compress the cold gas. So we have the usual formula, so it's simply the density times the temperature of the hot halo. And to make my analysis more easy, I'm introducing this beta parameter that is simply the ratio between the two pressures. And as you can see, it does not depend on the density of the hot halo anymore. So let's first take a look at the hot gas. So here you have the fraction of hot gas as function of time. And as you can see, in any cases, we remove the hot gas very, very fast. And we remove it faster than in isolation, which is the green line you can see here. But when we look at the cold gas, the situation is strongly different. We have a strong dependency on beta. So when we are dominated by the thermal pressure, we keep a lot of gas. And when we are dominated by the ram pressure, we remove it quickly. But as you can see, we remove the cold gas slower than in isolation, the green line. And that's simply because dwarf galaxies are dominated by the UV background. And in our case, the thermal pressure compresses the cold gas and make it dense enough to reach the self-shielding density limits. So the thermal pressure can protect against the UV background. But it also protects against the RAM pressure because having a denser cloud makes it harder to strip. So if we now turn towards the star formation, so we can see an enhancement of the star formation rate as seen in the non-classical point of view. And that's quite logical because if we keep more gas, we should be able to produce more stars. So from this study of wind tunnel simulation, I've been able to show how important it is to have high resolution simulation, to have this cold gas that behaves totally differently than the hot gas. So now we can try to move towards a more advanced setup that is called the moving box. The idea is to keep the wind tunnel setup, but to add some extra element. And this extra element is the presence of a host and an orbit. And by doing this, we can include the evolution of the wind parameters, but also the tidal stripping. And we need a model of the host to do so. So it's simply taken from observations of the Milky Way. And the evolution is computed from a simulation called LASTRO. We also need an evolution for the temperature of the hot halo. And this is simply taken from the virial theorem. So you can see the evolution of the three main parameters on the right. And as you can see, all of them are more or less correlated. And around 6 to 7, 8 gigayears after the Big Bang, we have more or less Milky Ways that correspond to the one we have today. But we also have the orbits, so we can also adapt the gas density of the hot halo according to the position on the orbit. So you can see here my model. So you have the density of the gas as function of the distance. So you have the line here that is my model, and the dots are observations. So as you can see, my model fits quite well the observation. And the last element we need are the orbits of the dwarf galaxy. So here I'm not trying to do a full study on the different type of orbits we have. So I picked only one that is compatible with Carina, Sextant, and Sculptor. So today the position is given here. And what we did is simply to integrate backward in time until the required redshift. So as you can see, you have two different points that are simply due to the fact that I'm using two different models for the host, one that evolves with time and one that does not. So here you can see the result of my different simulations. So each column corresponds to a different model of the host. In white, you have the galaxy, the simulation in isolation. And today I will just focus on the last line. So here you have the distribution of stars according to their iron abundances. And so the first column corresponds to a model where the host does not evolve. So it stays like we see the Milky Way today for all the evolution of the satellites. And as you can see here, we have a strong enhancement of the metallicity of our stars. And from the wind tunnel simulation I've shown you before, this is easily explained by the fact that we are dominated by the thermal pressure. This thermal pressure increases star formation rate, which increases the amount of supernovae we have, and so it increases the total metals we have within the galaxy. This kind of distribution is not seen in observation. So we need a better model to explain the observation. So here in the middle column, I try to improve the model by including the evolution of the mass and radius of the host. As you can see in this model, we do not really change the properties of the galaxy. And this is simply because the two parameters I changed are mostly impacting the tidal stripping, which is not very efficient for this galaxy with the orbit I picked. And again, this is not seen in observations, so we need even better model. So that's the last column, where here I'm changing the mass, the radius, and the temperature of the hot halo up from the host. As you can see, we recover what we had in isolation. So from this, we can clearly see that the UV background dominates the quenching of dwarf galaxies. And we also can see that we have an issue. If we come back to one of my graphs in the introduction, we can see that the environment should impact the properties of the dwarfs, which is not the case in the previous graph. So from this, I can tell you that it seems that the RAM pressure is not enough to explain that. And I think we are in the same situation than in the 90s. We still lack some physics to explain these graphs. And what I think we are lacking is the production of UV from the host. From my computation, the UV from the host around until distances of a few hundred kiloparsecs. So it could help to explain this graph. So to conclude this first part, I try to show you how important it is to have high resolution simulation to include the cold gas for the RAM pressure stripping. I try to show you how important the thermal pressure is to protect the gas against both the RAM pressure stripping and the UV background. And finally, I try to I present you my idea of the UV from the host that can play an important role to explain the environmental dependencies. So that's for the first part of my talk. So now I can move towards a far more technical part that is called the continuous simulation data stream. The idea is simply to redesign the way we write outputs from our cosmological simulation in order to be able to recover the state of the simulation at any time with high accuracy and for lower storage cost than snapshots. But before showing you how I do that, I need to show you why using snapshots is not a good idea. So the idea of snapshots is very simple. When you run a simulation, you let the system evolve for some time, and then you write the full state of the simulation into a single file. And then you run again the simulation for some time and write a second snapshot. And this does not take into account any kind of physics. Every part of the simulation is written at the same frequency. And in cosmological simulations, this is really an issue. So here on the right, I'm showing you a picture of the universe where the color represents the timescale you have. So in yellow, you have large timescales, and in purple, you have small timescale. So as you can see, a large fraction of the universe has large timescales. And only within the galaxies, you have very small timescales. So if we look at the distribution of particles we have within our simulation, we have most of the particles that have very large time step and a tiny fraction that has a very small time step. You can see exactly the same information with the number of steps required to reach redshift 0. So most of the particles will do only a small amount of steps during the whole simulation, while a tiny fraction is doing a large number of steps during the whole simulation. So using snapshots that write all the particles at the same time is not a good idea, because most of the particles will be written far too often, and a small fraction will be written not often enough. And to make it even worse, most of the time we are interested in galaxies, so where the time step are the smallest. So the snapshots are not designed to study galaxies. So as I told you, with the CSDS, I tried to implement a new technique that allows us to recover the state of the simulation at any time with a very high accuracy, and I try to minimize the storage cost in order to have a lower storage cost than snapshots. And to do so, I had to change the idea of writing files. So now I'm not writing a file for a given time. I'm writing one file for the whole simulation. And by doing this, it's very simple to write the particles at their own time scale within this file. And when we want to recover the state of the simulation, we simply need to interpolate the different fields we want to read from the CSTS. So to explain you how I do that, I need to show you the structure of the file. So we have one main file that is called the log file. And when we start the simulation, we start with a header, and then we write the initial time, and then we write all the particles within the initial conditions. Then for each step, we write simply the current time and all the required particles. And this is only the required particles. So they need to be active, but also need to match our writing criterion. And when we finish the simulation, we write again all the particles and conclude with the final time. It's very, very important to write all the particles at the beginning and end of the simulation in order to ensure that we will never need any extrapolation. So it might seem a bit ugly to do that, but we have a few tricks to make it cleaner and far more efficient. The main one is in the form of the records. So we use records to write any kind of information within the log file. So of course we have the data we want to write, so the position, velocity, and so on. But we have the header that contains two different information. The first one is a mask that tells us which kind of data are stored. So we have a mask for the position, one for the velocity, for the internal energy, and so on. So we can adapt which field we want to write at a given time, but we also can differentiate between the different type of particles and between a time or particle record. The second important information is called the offset, and it tells you where to find corresponding records. So for example, if we have this record P0, from the offset, we can quickly jump to the previous one, and from the previous one to the previous one. Unfortunately, it's not very user-friendly to go backward in time. So when we read for the first time the log file, we reverse all the offsets in order to point forward in time. So now we have a very efficient way of evolving the particles, but it does not mean that we have an efficient way of reconstructing the state of the simulation. For example, if a user requires the final time, we will have to read the whole log file in order to know which particles are still present, which one have been created, and to evolve all the particles to the final time. So we introduce some kind of snapshots that are called index files, and that will help us to speed up the reading. So we start with a header, and then we have one array per particle type. And we conclude with all the particles that have been created since the last index file and all the particles that have been deleted since the last index file. So within each of the array, and for each particle, we write only two pieces of information. First, the ID of the particles in order to identify them, and then the last known offset within the log file. So now from the index file, if we want the final time, we just need to go to the last index file, go to the last known position of a particle, and then evolve it a few times. So you might wonder why it's a good idea of having those kind of snapshots when I told you that snapshots should not be used for studying galaxies. And to answer this, I have two different answers. The first one is that the index files are a lot smaller than the snapshots because we store only 2 fields per particle and not a large number as we do in snapshots. And the second thing is that The index files do not contain any physical information. They are just present to speed up the reading. And so we can write them less often than snapshots. From my experience, 10 index files are largely enough to have good performances. Okay, so I've been mentioning this writing criterion, but I did not define it. So a very elegant way of defining it will be to simply use the error that will be done on the interpolation. So here you have a very classical formula for the interpolation error. But unfortunately, it will mean that we need to store some information for each field we want to write, and this will cost too much. So we decided to use a simpler approach that reuse something we already compute, and this is a timestep. Usually, this timestep is computed with equations that are similar to the interpolation error. So the users only has to provide us this n that tells you how many active steps are done between two writings. So now that you understand how the CSDS works, I can show you how good the CSDS is. So to do so, I've been running isolated disk galaxies run as dark matter only simulation. So we include only gravity and no hydrodynamics. And here you can see the relative error on the radius of the particles within this disk galaxy as function of the number of active steps between two writings. So on the left, we write the particles every steps, and on the right, we write them every 300 steps. As you can see here, when we decrease the number of steps between two writings, we converge towards a correct solution. And we can see that at 10 and 20 steps, we already have good results thanks to the quintic interpolation formula that I'm using. So we can see from this graph that the CSTS is indeed working, but we still need to ensure that it's better than snapshots. So here I try to reconstruct the state of the simulation using both the CSDS and the snapshots. So again, you can see here the relative error as function of the output size. So to change the output size for the CSDS, I'm simply changing the number of active steps in between two writings, and for the snapshot, the number of snapshots used for the whole simulation. As you can see, the CSDS is always more accurate and for lower storage costs than the snapshots. And for a given output storage, the CSDS is 2 orders of magnitudes more accurate than the snapshots. So we achieved what we were aiming for with the CSDS, but we still need to ensure that the CSDS can be used every day by astrophysicists, and to ensure that we need to show that it's not too slow. So here I run a different cosmological simulation. So those are the Millennium simulation at different resolution, both in terms of number of active steps between two writings and number of particles. So let's start with the scaling as function of the number of active steps between two writings. So writing every step, writing every 300 steps. So first, you have here the storage costs in orange. As you can see, the scaling is slightly lower linear scaling, which is what we were expecting. If you double the output frequency, you should also double the number of records, which means that you will need twice the storage space. Then we can look at how much time you need to read the CSDS. And you have 2 different cases. The first one is when a user requests a time that match an index file. And the worst case is when a user requests a time that is just below. So in the best case scenario, we just need to go to the index file and then read a single value in the log file for each particle. So it should not be dependent on the output resolution. And as you can see with the purple line, it's really the case. We always have more or less the same time. Then we can look at the worst case scenario, where in this case, we go to the index file, go to the log file, and then need to jump over and over until reaching the required time. So as you can see, we have only a moderate increase of reading time. You can even see the difference between the two lines here in green. And this is because most of the particles will do only a very small amount of steps between the two index files. So here, there is 1.2 gigayears between the two index files. And the average number of jumps required when we write every step is only 7. So as you can see, most of the particles cost almost nothing. Then we can look at the scaling as function of the number of particles within the simulation. And usually users expect everything to scale linearly. And as you can see, it's clearly the case. And you can also see in this graph that the CSDS has been tested with a simulation of 3.6 billion particles. So it's also work on very large simulations. The last piece of information that you missed from that is a comparison to the snapshots. So reading the full state of the simulation is about 10 times slower than from the snapshots. So I want to mention that those are still early results, so we can still improve the performances of the CSDS and decrease this gap. But anyway, we are still expecting the CSDS to be slower than the snapshot because the extra complexity costs us some time. But you can also see that the green line showing the difference between the best and worst case, so how much time you need to evolve the particles on very long time, is more or less 10 times smaller than for reading the initial state. So while it's not efficient to reconstruct the state every time you want to read some piece of information, the CSDS is more or less as performant than the snapshot when evolving the particles. So to conclude this part on the CSDS, I've been able to develop a technique that allows us to reconstruct the state of the simulation at any time with high accuracy and at a low storage cost. And before concluding this presentation, I just want to mention the project of a colleague of mine, which is called Reveap. So it's a high performance visualization tool developed for virtual reality. And so it shows very good performances on a personal computer with the Eagle simulation. So he has been able to visualize a whole simulation at 60 frames per second. And the reason why I'm mentioning this project is that we are planning to include the CSDS within it. So in the future, you might have a software that allows you to see the evolution of your simulation in live in 3D. So to conclude this talk, I've started to show you my result from the RAM pressure stripping. I try to convince you that we need high resolution simulation to understand what is going on. Otherwise, we lack the cold gas and cannot explain what is going on with the thermal pressure, and we can have wrong results. I've also spoken about my thoughts on the impact of the UV from the host on the RAM, on the environmental dependencies of dwarf galaxies. In the second part, I've shown you my result for the CSDS, where I can reconstruct the state of the simulation at any time and at high accuracy. So if you are interested into this technique, please feel free to contact me. You have my email address. And otherwise, thank you very much for your attention. And yeah. If you have questions, we can discuss them.
Great, thanks. I have questions, but I will leave the opportunity to the audience to ask first. So please, people in the audience, if you have a question, raise your hand, and I will give you the opportunity to have the question. For the moment, I cannot see. There is a hand raised here. Daniel, as soon as you want, you can turn on your microphone and you can ask.
Okay. Thanks for the talk. I have a question about the effect of feedback. Have you checked different models of feedback?
So the stellar feedback?
Yes, stellar feedback. I will naively think that if feedback is stronger, it not only can prevent the star formation, but also make the galaxy buffer more extended.
Yeah, I fully agree.
The operation can be more important.
I fully agree that we should study how the different type of feedback model should impact this. But that was not the main objective of this study. So I was really studying the impact of the pressure flow. But yeah, stronger feedback could push the gas further away and helps the ram pressure stripping to remove it. But what I can say about that is that our stellar feedback seems to be good when we compare cosmological simulation with observation. We are really able to recover what we see in observations. So yeah, I'm not sure if you want some additional answers, but that's not something I studied, but I fully agree that we should.
Especially if you have high resolution, you can resolve the feedback effect much better than in full box simulations with low resolution.
Yeah, I fully agree, but then you have an issue that your stars will all explode in supernovae in the same area. So when you have the first one that explode, you will push away your particles and reduce the resolution. So you even at high resolution, you still suffer from a lack of resolution around second generation supernovae.
Yeah, agree. Yeah. Thanks.
You're welcome.
Good. Thank you, Daniel. If somebody else has a question in the audience, please raise your hand and unmute yourself. Nobody. So I have a question about what you said of the homogeneous cloud and the way you are preventing this numerical collapse of the structures in the homogeneous cloud. I fully agree that we need to increase when we have this high resolution. We need to try to prevent these collapses, but also that in the real world you never have a completely homogeneous cloud. You have a small variations on the density. So what does the low resolution is to reduce the dynamical time for the collapse, but the collapse will be there anyway. Just the density fluctuations will be smaller. So when you are reducing artificially the collapse, have you tested at which limit you are reducing too much the collapse? So
that's really a hard question. So yeah, we did not really study this. But it's quite hard to define it because you do not have the resolution to know what is going on. So it's hard to set a limit. And as you know, clouds are almost fractal. So you really need to go to infinite resolution to know exactly what is going on. So we do not have the tools to do it and the computational power to really do it.
And the idea of using, for example, ISM simulations, pure ISM simulations with extremely high resolution, and there you get the answer that you need to apply to your models?
The issue is that we are really speaking about badly resolved stuff. So you will have only a few particles, and I don't really believe it's necessarily a good idea to make a comparison between a cloud resolved by 10 particles and a cloud resolved with billions of particles, because you will not necessarily have the same structures, same meticities, and so on. So it's really a hard question, and I think the only answer is just to try to have more efficient software, and in order to have a higher resolution.
Okay, interesting. And I have another one. Thank you for the answer. I fully agree also that it's a very complex stuff, this so-grid physics. And the other question is, you said that when you apply your model, what happens is that the cold gas remains for longer inside the dwarf galaxies, so you can produce more stars in dwarf galaxies. So this goes completely to the in opposite to solve the missing satellites problem. You are producing more satellites. So again, attention on the colder matter paradigm, no? Okay, I don't know if you have any comment on how bad is now the missing satellite problems after using your
So this missing satellite problem has been solved by people using low resolution simulation, or maybe high at the point in time where they run it, but not high enough resolution to really have this cold gas. So their models were designed for such simulations. So maybe we will need to adapt the models to solve it. So our model used some wrong assumptions. And as you can see from this simulation, so here we do not really go away from solving the missing satellite. We just stop solving it, if you want. We don't go to the opposite direction. It's just that we do not have any environmental dependency. And as I've mentioned, I really think that the key element is radiative transfer in our simulation. So we really need to include the UV from the host that will boost the UV background and help to quench dwarf galaxies close to the host.
Also, maybe these systems are so small that you are only forming few stars with this cold gas. So maybe observations are still not there to observe this.
Yeah, it's a small system, I agree, but still we do have a sculptor that is not an ultra-faint dwarf galaxy. So with dwarf galaxies, we should be able to see this kind of things. But yeah, we do not have radiative transfer, so a colleague of mine is working on it. So I'm hoping in the future we might have some result with this UV, this UV from the host. And in fact, you don't even need to go this far. So I wanted to start, but never had the time to do so, is to improve the moving box by including the UV from the host. So you can just use the same descriptions in the UV background, but simply add a radial dependency and time dependency on it.
It's interesting also that this thing of adding the ultraviolet from the host, because if I remember well, I don't know if it was 2014 or 2015, there was a work in where they said that basically the local sources for the ultraviolet background are in fact not really important for this. I am not sure. I need to revise again this work, but I'm not sure if the ultraviolet background from local sources can be the solution. Maybe also Daniel can say something about that, because I had discussions with Daniel about the local sources of ultraviolet.
So I'm just wondering, the paper you are mentioning is mostly interested in normal galaxy, not dwarfs, right? So that might be a difference.
Yeah, that's true. It was for Milky Way mass galaxies, if I remember well.
Yeah.
Daniel,
that's always difficult thing to address, right? There's always some internal processes, some radiation that was emitted within the galaxy that affect the dwarf, right? And also external radiation. So it's difficult to see which one is more important.
Yeah. And something I did not mention is the numerical methods for hydrodynamics. As you know, from the Agora project, is just a mess to compare them, and you have so different behaviors depending on the methods. So something that will be interesting is to redo the same study, but including different hydrodynamic methods. For example, I'm expecting AMR to have less this issue than SPH, because there is this over how do you say it in English? So the AMR is mixing far too much the gas.
Okay, yes, I agree that it would be great to have this comparison also within Agora. And related with using different codes, my last question is for the CSDS. You said that you want to release it together with this visualization tool to the community. Does this support all different codes? Is only for SPH for the moment, or you have plans to expand it?
I design the CSDS for SPH. So currently, I will say, if you know your code, it's easy to implement it in SPH. For AMR, I think you can still use the same technique, but you will need to change a bit how you do stuff, because one of our main advantages in SPH is that if you forget about star formation, we are not creating particles. So we can follow them and they move through the simulation. While in AMR, your cells are fixed and you need to create, remove cells. So I really think that going in the CSDS direction is a good idea, but you will need to adapt it for AMR.
It's extremely complex. I don't know if it is possible. I would say that maybe not for the mesh, but for the particles, for a pure, probably you can make an adaptation to the gravitational part. I don't know if this would be useful or not, but yeah, of course, for the AMR could be extremely difficult to use.
I'm not sure difficult, because that's a question I've been asking myself for some time. And I think what you can do is simply to write in the log file when you create new cells, and then you don't write the position, you just write the cells whenever you need to. And in fact, it makes it more simple because you don't have to deal with the position anymore. So you can still have this approach where you write the cells at their own timescale.
Yeah, it would be. Well, I have to think on that, but well, we can just stay in touch about it, because also visualization looks amazing. So to have this tool always is good for all the groups.
Yeah, so the one behind the software is Florian Cabot. He's working for Heave, so feel free to contact Heave if you are interested in running it.
Perfect. Okay, so I will give now the opportunity again to the audience if somebody else has a question. And if not, we will leave it here. It's almost 11 now. So, okay, nobody else. So thank you again, Loic, for the very nice presentation. And also thank you for sharing your results. And we hope to see, although you are in the private industry now, we hope to see more results of science. You told me that you are still doing some science, no? So
yes.
We hope we can see some new science from you in the future. And thank you a lot for accepting the invitation. And for the people in the audience, thank you for coming to this last IPARCOS seminar of the year. We will have new seminars for the spring season. We are organizing it, so stay tuned. And I think nothing else, just to wish you a very happy holidays, happy Christmas holidays, and see you next year.
Yeah, thank you very much for the invitation. Happy Christmas and see you.